Next, we'll talk about moving data in the network. Data encapsulation is what we're going to talk about. In theory, a single communication such as a music video or an email should go as one unit. However, they're too large to do that through the system, so they have to be segmented and the data has to be encapsulated. A better approach is to divide the data into smaller, more manageable pieces to send over the network, and this division of the data stream into smaller pieces is called segmentation. And once we're segmenting the messages, we have two primary benefits when we do this. By sending smaller individual pieces from source to destination, many different conversations can be woven together across the network, and the process used to interleave or weave these pieces of separate conversation together on the network is called multiplexing. Segmentation can increase the reliability of network communication, and the separate pieces of each message doesn't need to travel the same pathway across the network. Each piece can get there the quickest way it can, and then it's reassembled in order because they each have their own information in the header so that it knows in which direction to put it in. When we segment information, this demonstrates that where the piece of mail goes from the person who is sending it to the server one piece at a time. Multiplexing allows both individuals to send information, and it goes as small segments, and then once it gets to the server is going to put those pieces back together. As application data is passed down the protocol stack on its way to be transmitted across the network media, various protocols add information to it at each level so that it knows it's gone through that particular piece of the protocol and it's added a little bit more to it. This is commonly known as encapsulation. The form that a piece of data takes at any layer is called a protocol data unit, or a PDU. And during an encapsulation, each PDU that it receives from the layer above, in accordance with the protocol being used, it's given an additional piece of information. So as it's going through the protocol, we have data, and that's the general term for the PDU used at the application layer. Then it becomes a segment, and that is at the transport layer. A packet is the network layer PDU, and then bits is a physical layer PDU, and it's used when physically transmitting data over the medium. Data encapsulation is also the process that adds additional protocol header information to the data before transmission. In most forms of data communications, the original data is encapsulated or wrapped in several protocols before being transmitted. So at each step, it kind of gets its stamp of approval. It's been here. We're going to add this saying that, yeah, we saw it, and it now can get passed along. You saw this earlier when we went through the protocol encapsulation, where it went from the web server, and it was the data PDU. Then it became the TCP segment. Then it became the IP packet. And then finally it becomes the Ethernet frame. This process is reversed at the receiving host end. It unwraps the package. It checks off all the places that it went, and it takes each of those pieces away. Here's an activity that you can use to see if you can figure out where the information goes. Just drag and drop wherever you think the information needs to be, and then you'll check it and see what you got right or what you got wrong. And you can rearrange them and check them again. This is a great learning tool, the different activities throughout these units. Now, accessing local resources. The OSI model describes the processes of encoding, formatting, segmenting, and encapsulating your data for transmission over the network. And the network layer and the data link layer are responsible for actually delivering the data from the source device or sender to the destination device or receiver. And protocols at both layers contain source and destination addresses, but their addresses have different purposes. With the network address, the network layer or layer 3 is a logical address, and it contains information required to deliver the IP packet from the source device to the destination device. And a layer 3 IP address has two parts, the network prefix and the host part. The network prefix is used by routers to forward the packet to the proper network, and the host part is used by the last router in the path to deliver the packet to the destination device. An IP packet contains two IP addresses, the source IP address, that's the IP address of the sending device, and the destination IP address, that's the IP address of the receiving device. And the destination IP address is used by routers to forward the packet to its destination. You can see that referenced in this diagram over here. The data link address is your layer 2, and it's your physical address, and it has a different role. The purpose of the data link address is to deliver the data link frame from one network interface to another network interface on the same network. Before an IP packet can be sent over a wired or wireless network, it must be encapsulated in a data link frame so that it can be transmitted over the physical medium, actual network. And in it we have the source data link address, and that's the physical address of the device that is sending the packet. Initially, this is the NIC, or the network interface card, that is the source of the IP packet, and then the destination data link address, and that's the physical address of the network interface of either the next hop router or the network interface of the device. Next, to understand how communication is successful in the network, it's important to understand the roles of both the network layer address and the data link address when a device is communicating with another device on the same network. Okay, they're on the same network. The network layer address, or the IP address, indicates the network and host address of the source and the destination. The network portion of the address will be the same, because they're on the same network. If they're on different networks, then that would be different, but this is addressing it on the same network. So the IP address of the sending device, the client computer for PC1, here is its IP address, the 192.168.1.110, and the destination is the 192.168.1.9. When the sender and receiver of the IP packets are on the same network, the data link frame is sent directly to the receiving device. On an Ethernet network, the data link address are known as the Ethernet MAC addresses, and the MAC addresses are 48-bit addresses that are physically embedded on the Ethernet NIC. And a MAC address is also known as the physical address or the burned-in address. Your source MAC address, this is the data link address or the Ethernet MAC address for the sender. And the destination MAC address is the MAC address of the destination that the packet's headed. The source and destination addresses are added to the Ethernet frame. The frame with the encapsulated IP packet can now be transmitted from PC1 directly to the FTP server here in this example. It should now be clear that to send the data to another host on the same LAN, the source host must know both the physical and logical addresses of the destination host. Okay, so they have to know the MAC address and the IP address. Most network applications rely on logical IP addresses of the destination to identify the location of the communicating host, and the data link MAC address is required to deliver the encapsulated IP packet inside the Ethernet frame across the network to the destination. And here's an example of that happening. The sending host uses a protocol called ARP, or Address Resolution Protocol, to discover the MAC address of any host on the same local network. And the sending host sends an ARP request message to the entire LAN, and the ARP request is broadcast. It means it goes to everyone. And the ARP request contains the IP address of the destination device, and every device on the LAN examines the ARP request to see if it is its IP address. And once it receives the IP address that belongs to it, then only the device with the IP address contained in the ARP request responds with an ARP reply. It's kind of like a handshake. It's like, hello, how are you? I'm fine, I got it. Now if we look at a sender sending information across to its destination and they are not on the same network. The method that the host uses to send messages to a destination on a remote network differs from the way a host sends a message to the destination on the same network. When a host needs to send a message to another host located on its same network, it will forward the message directly, because remember, it had sent out the ARP request and it had learned everybody's MAC addresses and it knew where it belongs. When a host needs to send a message to a remote network, it must use the router, also known as the default gateway. And the default gateway is the IP address of an interface on a router on the same network as the sending host. Okay, so the sending host and the router's IP, or the interface, are on the same network. The router can have other interfaces on a different network. It's important that the address of the default gateway be configured on each host of the local network, and if there is no default gateway address is configured in the host TCP IP settings, or in the wrong default gateway is specified, message addressed to host on remote networks can't be delivered. In this figure, the host on the LAN are using router 1, or R1, as the default gateway with its 192.168.1.1 address configured in their TCP IP settings. If the destination of the PDU is on a different IP network, the host sends the PDUs to the default gateway on the router for further transmission. Once it hands it off to the router, now it's the router's responsibility to keep going. What are the roles of the network layer address and the data link layer address when a device is communicating with a device on a remote network? Well, the IP addresses indicate that the network and device addresses of the source and destination. When the sender of the packet is on a different network from the receiver, the source and the destination IP addresses will represent that. Your IP source address is the IP address of the sending device of the client, PC1, and the destination address. In this example, it's going to the web server, and the IP address of the receiving device. And you will see that they're sitting on two different networks. The data link address, when the sender and receiver of the IP packets are on different networks, the Ethernet data link frame cannot be sent directly to the destination host because the host is not directly attached or reachable through that network. The Ethernet frame must be sent to another device known as the router or the default gateway. In our example here, our default gateway for the PC1 is R1, and the default gateway for the web server is R2. So our source MAC address is the Ethernet MAC address of the sending device, PC1. Then we have our destination MAC address. When the receiving device is on a different network from the sending device, this is the Ethernet MAC address of the default gateway or the router. In this example, it is R1. Once R1 gets it, then it adds more information, sends it to router 2, and then router 2 can send it on to the web server. So it's important that we get all of our little pieces of our address correct. You will work on your packet tracer, explore network instructions, and using Wireshark to view network traffic. Now when you work on this particular lab, make sure that you load it clean with no configs when you make your reservation. You are only going to be able to ping between the PCs. You will not be able to ping the web addresses that the assignment gives you because NetLabs does not allow access to the internet. Good luck with this chapter. Make sure you do all the activities within this online material. It will be helpful, and you will see it again on exams.